see if I can stay live this time. The triple bond shows up in that pretty much dead space in between. So you'll almost never see anything there unless there's a triple bond, in which case you see a nice sharp peak. Okay. So that's why I typically don't look for the CHSP hybrid. Okay. It's also fairly rare, so it doesn't show up all that often.
So that section is what?
It's pretty much a dead zone. So pretty much the only thing you'll see there will be the triple bond, a carbon something triple bond. Okay. So I don't look for the CH. Yep, exactly right. I won't look for the CH where that carbon is sp hybridized because I can find it easier by looking in that triple bond range. Okay. So that was a good one. I wasn't considering that one. What else? There's another one. What's that? Aromatics. Aromatics will actually show up the same as a CHSP2. So that's not unique. I know the two of you in back know this one. What was the NH? What's that? NH is not a CH type, but it does show up in that range. You got the right idea. Nope. Come on. Closer, and you guys just did this one. No. Aldehydes.
Oh.
The aldehyde hydrogen shows up fairly characteristically, oddly lower than the CHSP3s. Okay? So if we look at an aldehyde, that's our functional group. That bond, our CH bond there, even though our carbon is sp2 hybridized, shows up lower than our CHSP3s, and it's also a pseudo-dead region. Okay? How would you be familiar with what each of these individual signals look like? Okay, so some of it's practice. That ultimately is going to be your memorization, but how are you going to get that practice? There's an easier way. There might be someone out there that was kind enough to take images of each of those types of bonds and classify them and say what each of those bonds might look like, and then post that information for everyone to have access to and use. Okay? You should use that information, and then IR becomes just a matching game. You are already told what each of those individual signals look like. You just have to match them up. Okay? There are exceptions to that. Things shuttle around a little bit, but it helps. Okay? I do not recommend the tables. Okay? Because the tables lose a lot of information about the intensity of the signal and its shape. Okay? And that information doesn't translate well into English. In English, it becomes it's broad or intense or weak or moderate intensity. So it's too vague to really become useful. Okay? So until you're comfortable with recognizing or interpreting IR spectra fairly rapidly, until you've had that practice, I would recommend that you have that background sheet in front of you when you go through and process. And just match. That's all it is. Hey, that looks like a star. Okay, it's a star. Right? That's it. Okay? Try to make it as simple as you possibly can when interpreting the IR. Yep, I'm going to have to yell at them about their software. So when it comes to NMR, I've got it written here as 4 things that we can look for. 4 bulk things to determine. And I've got them ranked according to easiness of interpretation. Okay? So when you look at an individual spectrum, you should be looking for each of these kind of bullet points and trying to interpret them to the best of your ability. Okay? Come on, work. Go figure. So when we start off with, when you look at either carbon or HNMR, we can take a look at the number of signals. Okay, not the number of peaks, but the number of signals. I'll classify that when we look at an actual spectrum. That's going to give you information as to the number of unique hydrogens or carbons. Okay? And we talked about unique as just being chemically different. One of the best examples I can think of is if you built the model, okay, remember that 3 or single bonds can rotate. If you built the model, picked a hydrogen, and spun it around and then spun all the bonds around as best you can, tossed it, turned it over, threw it in the air, sat on it, whatever you wanted, would you be able to identify that exact same hydrogen? Okay, after all of that process. If you can, that hydrogen is unique. If you can't, it's not unique. Group it with the hydrogens that are similar to it. That shows as one signal. Okay, makes sense? Same applies for carbon. Okay, same general idea. The next thing that we can get is chemical shift. This gives us a rough approximation to the local environment of our hydrogen or carbon. Okay, so again, use this kind of like you would use IR. Do you see a signal within certain ranges of your chemical shift? That means some structural information. Very, very minimal. When we go through and solve problems, I'm going to treat it as it's the atom to which the hydrogen is bound. Okay, and just the atom, nothing beyond that. Okay. The next piece of information is your integration. There's a lot of different ways you can see the integration. I believe exclusively in your packet, it's shown as the not reduced ratio underneath each of your signals, or underneath the series of peaks. Okay. It's usually a not very nice number, something like 13, 23, 23.4. Okay. So what you need to do is get that into something that makes a little bit more sense. So you can convert it to the reduced ratio, find the smallest integration value, divide everything by that number. Okay. If you're lucky, the numbers come out somewhat reasonably and you can do that division in your head. If you're not lucky, use a calculator. Okay. And that will give you that integration information. With that, that tells you about the number of hydrogens that that signal represents. Okay. Closely or similarly to that. Okay. If there's symmetry in the structure, it's not directly the number of hydrogens, but it's a multiple of that ratio. Okay? The very last thing that we talked about was the multiplicity or splitting, and this gives us information about neighboring hydrogens. Okay? So it's an important point to note here. When we look at integration and multiplicity, what are you laughing at? Oh. The integration and multiplicity only refer to hydrogen NMR. Okay? And yes, as you've already noticed, the splitting patterns tend to be the most difficult, and I've noticed that students like to jump to integration and splitting as far as interpreting and confuse the two. Okay? Which is why it becomes very difficult to interpret, because you start shuffling different numbers around. Okay? So try and keep those separate. The splitting or your multiplicity is the number of different, or the number of peaks that you see within an individual signal. Okay? That can be related to the number of different hydrogen neighbors. Okay? So we get a relationship here of the number of peaks. And that's going to be equal to something about our neighbors, the number of our neighbors. And our rule is neighbors plus 1. Okay? So if you have your spectrum, you can then convert the number of peaks over into the number of neighbors. In some cases, it's easy to see what number of peaks there are. In other cases, it's a bit of a mess, and you kind of have to use your approximation skills. Okay? To the best of your abilities. What defines a neighbor? What did we say last week?
3 bonds.
Okay. A neighbor is within 3 bonds. Not necessarily that. So it's a unique hydrogen within 3 bonds. Typically, it's 3 bonds away. Okay, that's the standard. Probably 95% of the problems you'll see, it is 3 bonds away. Okay, and that last 5%, it can be on the same atom. Okay, that you can still have a hydrogen that's chemically different than the other one. Okay, and that gets a bit tricky. And I think I might have picked a problem where we can see that. Okay, in here. Okay. So those are your big 4 things. So when you go through and interpret, try and start simplest first and work your way to the more difficult. One of the things, again, that I would recommend that when you go through and do this, is instead of jumping to integration and multiplicity, put the information that you know down first, okay, and start writing even though it's simple. Okay, get that information down. Once you've got the structure, the pieces there, it starts to become easier to put together. Okay? If you wait to start putting pieces together in your head, you're going to mess it up.
So when you say rough local environment, you mean like the 0 to 2 alkanes?
Yep. So between 0 to 2, if you see a signal there, what the chemical shift tells you is that that hydrogen, which you got from there being a signal, okay, so if we see any signal, we have a hydrogen. That's our first interpretation. We then look at the chemical shift. If it's between 0 and 2, that hydrogen is bound to carbon. That's the rough local environment. It tells us what atom that hydrogen is bound to, or some information about that atom. Okay? Yes?
When we're doing the multiplicity, would it help if we have a model kit to put it together?
Models can help. I've never used a model when dealing with NMR. If it's something that you think will help you, then absolutely use it. But I would be kind of surprised. Okay? So what we're going to do is slowly work through a compound. Did it switch now? Okay. So we're going to slowly work through an individual spectrum. Okay? In this case, I'm telling you it's a carbon NMR. How would you typically notice that? You'd look at your chemical shift along the bottom, and we would see 0 upwards of 200. Okay? Along that y-axis. That's an x-axis, just so you know. So our first interpretation, we see 2 signals, which means 2 unique carbons. Okay? That's a nice thing for you to observe. Okay? Imagine now that you have to grade your work. Okay? If you go through and conclude that and don't write it down, I don't know that you know that. As simple as that observation may have been, I have no verification of that. So you need to write down, as silly as it may be, 2 unique carbons. Okay? Yes?
Does it matter the height of the peaks or just any
We'll
at all?
move through that in a little bit too with our carbon NMR once we get a little bit further into it. Okay? And now it's going to delete all my work, but that's okay. So we can look at the next piece of information, which is our chemical shift. Okay, to see the chemical shift, we have to look at our values on the x-axis, and it looks like I hid them from view. So we can now drop those in and now evaluate those. Okay? So we had 2 unique carbons. Where are those carbon peaks? Our signals, they're roughly between 30 and 20. Okay? What does that tell us about our local environment?
Okay.
It's alkanes. How do we know that?
0 and 50?
You look at the table that says between 0 and 50, it's alkane. So it's a very simple, just direct comparison. Okay? So, what was your question? You asked about peak height. Okay, so that's an interesting, valid question here. So when we go ahead and take a look at the actual spectrum, you do notice a difference in peak height. Can we interpret it? Okay. What I said on the previous slide was that integration, which is ultimately our peak height, is only for hydrogen, not for carbon. Okay. Does that mean there's no information there? Kind of not really. That peak height, it can be related back to the number of other large groups attached to the carbon. The shorter the peak, typically the larger the things attached to that carbon. Okay, so if you have a tertiary carbon, the intensity of that signal ends up being very, very small. Okay, because it's buried behind a bunch of extra electron density and we don't pick it up as easily. Okay? I'm not sure that's a good explanation, but that's true. The more things around that individual carbon. So if we looked at, let's see if I can draw on this. If we compared out this compound, how many unique carbon signals would we expect to see? Go ahead and add a hydrogen. We'd expect to get 2. Okay, these carbons are all the same, and then our one in the middle is different from it. Okay? So we would expect, again, alkanes, nothing particularly fancy about it. We might expect a signal or signals very similar to what we've got shown up here. Okay? Our boxed carbon is connected to 3 other carbons. The more things attached to it, the shorter that signal becomes, so that if we were actually going to guess at this, we might actually see something along the lines of a short one and a tall one. Whoops, I didn't mean to draw that in the same spot. Okay, and a tall one next to it. Okay? Does that kind of make sense? So don't analyze or heavily analyze the peak height when it comes to carbon NMR, but sometimes you can get lucky and pick some information out of it. Okay? Questions about carbon NMR? If we can't do peak height, are we going to do multiplicity? No. Okay? So peak height is integration, or similar enough to it. Okay? So we won't worry about our multiplicity or integration data when it comes to carbon NMR. Okay? There are other types of NMR spectroscopy that we're not looking at this semester. If you take a look at your textbook, they talk about some versions that incorporate some splitting patterns. Okay? You can evaluate your textbook for that. We're not going to talk about it. One more thing that I'll point out on this is you notice that we've got CdCl3 marked here as solvent. There's 3 little peaks. Okay? When we run NMR, your solvent, or you always have a solvent present. Okay? That solvent is there to help dissolve the compound and make sure that our instrument can average out motion out of our individual samples. Okay? It typically shows up in each of the samples, assuming it's not digitally made. This one was actually digitally made, so that is actually hand-drawn in there. Okay? In a carbon NMR, the chloroform shows up as 3 peaks centered at about 77. Okay? That handy-dandy little packet that I've also got posted to Canvas tells you where those solvents show up. Yes. Okay? Working yet? Nope. So we can move to HNMR. Okay? So again, you'll notice that we've got, again, this kind of weird box and just 2 signals shown on it. Okay? Because what I'm trying to get you to do is to focus just on the groups of signals, not on the overall spectrum. So when we look at this, what information do you tell me? There's 2 hydrogens. Okay? We could write that up in our upper left-hand corner, just like we did with the carbon NMR. Last week I went through and showed saying we've got a hydrogen and a hydrogen, drawing it next to it. Okay? We'll go through and do some version like that, and I'll show you another way to organize your thoughts with some of the later ones. Okay? So we've got 2 unique hydrogens. So we could move to the next one, or the next piece of information. Yeah, this is really messed up. Okay? We've got our chemical shift. We're looking at that 0 to 14, technically range. Why did this not go all the way up to 14? There's nothing up there, so we don't need to worry about it. Okay? We're looking 0 to 14, so we're probably looking at HNMR. So we can now analyze our peaks and try and decide where those things are. Okay? So our hydrogen on the, what is that, right? What can you tell me about that hydrogen? What is its local environment most likely? It's probably an alkane. We're looking at a carbon. How about the other one? Okay? It's in that everything else category. Okay, so what should you write then? Okay, you could write pretty much anything you want. I almost always write an X, okay, until I can figure it out. Once I figure it out, I'll erase my X and put another letter in there. Okay? We do have some ways to limit that. What can X be? As a hint, there's only 3 things it can be for this class. Carbon, oxygen, and nitrogen. Those are the only 3 things you've got to be concerned about. Okay? Why would it not be a halogen?
Because
halogens can't make a second bond. Okay? It could be sulfur, phosphorus, and all that, but organic chemistry will skip that for the most part. So now what we can do is look at the integration, which can be related back to peak height, but not always. So you need to be a little bit careful about that. I tried to draw this one out so you could kind of see the lines on this one. You'll notice there's a crease partway through some of this. That crease is supposed to show how I ended up drawing this. Meaning, what would our integration be?
2 to 3.
It's roughly 2 to 3. From your spectroscopy packet, more than likely what you would see would be probably something like 21.3 to 32.3. I think I did the math right. Okay, so you would just divide both of them by that 21, get your ratio. It won't come out perfectly always, but it'll come out pretty close to whole. If it looks like you hit a half, multiply everything by 2. Okay, that's also usually fairly rare. So like I said, the peak height only works, or I didn't say this, but the peak height only works if it's a straight, perfect line. Okay, we're in a real world situation. It's not going to be straight and perfect, so what we have to do is instead evaluate the peak area. Okay, so the actual signals look something along these lines. Okay, why didn't it go to multiplicity already? Oh, that's why I went to multiplicity. Look like this, so we can't directly measure height, so instead we're going to have to look at the integration or the area underneath the curve. It's a little bit difficult to calculate, so we usually make the computer do it for us. Like I said, variety of places to see it. We just talked about one being directly under it with those bigger numbers. You could see it as this sloping line. That was the old way to do it. We would measure then the height of that line and then compare that across the height of all the other lines. Okay, because the computer would calculate the integration for each of those. Okay. Typically now you either see the number underneath, or if the structure's really nice, you'll see numbers written next to it, giving you that 2 to 3 ratio. Okay. That gives us some more information about our structure. So if we were going to continue going through and summarizing as we went, to begin with, we said we had hydrogen bound to some atom X for that one. For the other one, we had a hydrogen bound to carbon. Okay. Last week, I said you could interpret whichever signal you wanted. This week, I'm going to tell you I would start with multiples of 3. Why would I pick multiples of 3? Or integrations of 3? Because more than likely, if I've got an integration of 3, that means I have a methyl. Okay? There's only one bond that's missing in that case. That helps me go through and interpret, makes it a little bit easier for me to understand. Okay? As opposed to starting with something that had an integration of 2, because now in theory there's multiple different positions that are left open, particularly if that's a carbon. It's a lot more difficult for me to interpret, so I'll pick the easy stuff first and hope the easy stuff solves the hard stuff for me. Okay? Kind of makes sense? Okay. If we move to the other signal, we said an integration of 2. So instead of it being HX, what does it need to be? It has to be H2. Does that give us any information about the identity of X?
It's not oxygen.
It's not oxygen. Oxygen can only have 2 bonds when we're running our spectras, okay? Because otherwise it's an ion, and that's usually a bit wonky, except for one of the problems in your packet. Everything will be neutrally charged. Okay? So oxygen can no longer be atom X. So we're now confined to nitrogen or carbon. So that can be helpful. Now we're starting to build our pieces outwards. We'll go in and look at our multiplicity. Okay, this is looking at the number of peaks equaling our neighboring hydrogens plus 1. So as far as the multiplicity goes, let's go ahead and color change for this case. Again, I like starting with my 3 hydrogen signal, so I'll stick with that one. How many peaks do we see for that? 3. So if I've got 3 peaks, what does that mean my neighbors are? I have 2 neighbors. So what I can go through and do is say that some atom X has 2 hydrogens attached to it. Okay, so I've now added some extra information to my overall structure. Does that make sense? Okay. What is atom X? Okay. We have the potential for it being a nitrogen, okay, but there's one extra little piece that's nice from multiplicity. I'm not sure if I remembered mentioning this or not. Nitrogen and oxygen are kind of special. What do? They hide hydrogens. Meaning, if atom X, in this case, our blue atom X, was a nitrogen, they would not count as neighbors. The hydrogens attached to it would not be able to split my red hydrogens. Which means we already got rid of it being oxygen. I have splitting, which means it can't be nitrogen. Atom X, in this case, or my blue atom X for the moment, has to be a carbon. Wow, it's a really big eraser. Okay? And I can add that extra little bond out there. Okay? We can then go back to our other sample, our other signal. We've got splitting. What does that mean about the identity of our red atom X? It must be a carbon. So we can go back and now quickly edit that out and make that a carbon. Okay. Next piece of information from our splitting, how many peaks do we get? 4, which means we need 3 hydrogen neighbors. The easiest way to get 3 hydrogen neighbors, we'll put in a methyl. Okay. As far as our HNMR goes, that's all we've got. Okay. Which is a bit problematic. What's the structure of our compound? Okay, what was that's a formula.
What is the structure of our compound?
What's our structure of our compound? Does that work? How about that? Maintains the same ratios. Doesn't invalidate our carbon NMR. We could try and go through and say, I'm going to now, instead of drawing out our formulas, go a little shorter. We could do something like this, because now that center carbon keeps these as the same, but we've now added a carbon. So if we went back and looked at our carbon NMR, we'd have a third signal. So this one doesn't work. Okay, so how would you solve this problem? You have to be given more information. Okay? What other information were you given? The molecular formula in your packet. I didn't give it to you here intentionally. And the molecular formula says what we've got is C2H5Br, which means there's our final compound. Okay? So HNMR ultimately gives you a lot of pieces. Okay? Anything that has hydrogen in it. But if your structure has something in it that doesn't have hydrogen, H&MR is not going to tell you it. Okay, so you have to find that information somewhere else. Okay, kind of makes sense? Yes.
The number of peaks, it is a neighboring hydrogen plus 1.
Yes.
So there's 4 peaks, there's going to be 3 hydrogens.
3 hydrogen neighbors
And plus 1.
to here. So that's how we get the number of peaks. So if we've got 4 peaks equals the number of neighbors plus 1. How many neighbors do we need to have then? So if we solve for neighbors, we would have 3 neighbors. So when we go back and draw out our structure, so that was our CH2. According to our multiplicity, it has to have 3 hydrogen neighbors. So we'll make a bond out. That has to be a carbon, and that carbon should have 3 hydrogens attached to it. There are 3 hydrogen neighbors. So if we looked at our 3 bond rule, in green now, 1, 2, 3, first hydrogen neighbor, 1, 2, 3, second, 1, 2, 3, third. Does that make sense?
Yeah.
Okay. Questions about that? Yes.
Can you go over again how you eliminated the X and got to C? Just really quick.
So the reason I was able to decide that that was a carbon was because I looked at the multiplicity and I had splitting. Oxygen and nitrogen hide hydrogens, preventing splitting. So if you see your signal split, that hydrogen's attached to a carbon. So if we look here, that signal is split. The hydrogens represented in that signal, our red hydrogens, must be attached to a carbon. Split into those different peaks, yeah. Victor, did you have a question?
Oh, so you're saying that oxygen hides, oxygen hides hydrogens, so you would see the H in OH?
So it's not that you don't see an OH. You would still see a signal for an OH. But if you were within 3 bonds, so for instance, if we went back to this, since we didn't, we did look at an IR. Let's say you didn't have the IR, and this was your formula. Let me just erase all of that, clean up. I probably shouldn't have erased that part. Oh well. And your formula was C2H6O. So instead of it being a bromine, we could say, oh, it's an OH. Okay. So what we would expect in our H&MR is another signal. Okay. And if we evaluate the bonds, if we look for our neighbors, that hydrogen has 1, 2, 3 bonds. That's a hydrogen. That should count as a neighbor. We would expect that to split, except that this oxygen prevents that interaction.
The same thing with nitrogens?
And the same thing with nitrogens.
So what that signal look like?
Single peak. So that hydrogen would only show up, our alcoholic hydrogen would show up as a singlet, 1 peak. Okay. Depending on hydrogen bonding, okay, so if we had a lot of hydrogen bonding in that solution, what might we expect to happen to our signal? So what is hydrogen bonding saying? It says I take an oxygen over here and I interact. What does that do to the strength or weakness of that bond? Does it change it? Yep. So what ends up happening is instead of seeing a nice individual single peak for only a single bond energy or a single environment, I end up seeing multiple signals around it. But I can't characterize those signals, so instead what happens is the instrument graphs it as a broader signal. So when you look for an alcohol, typically your alcohol, your OH, your hydrogen from an alcohol shows up as a broader signal. Okay? Take that even further to a carboxylic acid. That bond is so weak that that hydrogen comes on and off very, very fast, hence it's an acid. What happens to the intensity of a carboxylic peak? It virtually becomes indistinguishable from the baseline. you have to zoom in so much that your peak is usually stretched all the way across. So you see such a subtle change in it that if you don't zoom in on the baseline, you won't see the signal. Yes?
How would you distinguish the difference between an OH bond and an H?
They both show up very similarly in the HNMR. Okay, they both tend to be broader. They're both going to show up as singlets, but what might be a characteristic difference? How many bonds can a nitrogen have? So if we looked at an integration, our integration would probably jump up to 2 versus 1. Okay. If it was a secondary amine, so it was attached to 2 carbons, how would we be able to tell the difference? We wouldn't, really. Okay. And we'd have to rely on other information, like our molecular formula, to give us that. Okay. More questions about that example? Okay, so the very last thing that we would do, sorry, I forget, I can't do it on this, just do it here. We would compile all the data. So this is where you would go back through, look at your IR, your mass spec information. So in this case, I kind of hid it from you, but have now told you. You take a look at your carbon NMR, your HNMR, and try and put things together. From our HNMR, we had these 2 sets of data. If we compare that back to our mass spec says we only have 2 carbons, which means what's wrong with our HNMR? We duplicated. So, can this CH2 be any other CH2? Yep. Which means what we can do from our HNMR is immediately eliminate one of those. Now, do we have all our correct pieces? Officially, we have the CH3, CH2, and we have a bromine, which we learned from our mass spec as well. Okay, how can we put those 2 pieces together? You just attach them. Okay, so your best process to go through, summarize everything, get everything compiled, go through and eliminate discrepancies, okay, as best as you can. Then you'll be left with at most 3 or 4 pieces. Those 3 or 4 pieces, in most conditions, you can only put them together one way. Okay, there's only one possibility. The one big exception to that is if you think you have an ester functional group, there's 2 ways to put together esters. So you have to look at your HNMR very, very, very carefully to be able to interpret which ester you end up having. Okay? Questions? Okay, so let's see if we can try examples, because I think now that's all I've got. Okay, so if this is the information you're given, oh, I meant to put formulas in here. So we'll do it without formulas. Tough. Okay, bless you. So where should we start?
IR.
Start with the IR. What do you see in the IR? First off, where is the IR? Which one? Top right, good. You see anything else?
Is that 2 OHs?
So I was kind of waiting to see if anybody called that one out. That signal is actually an overtone signal from the carbon-oxygen double bond. So if you see that, that's usually a red flag that you have a carbonyl. Okay? Don't treat it as anything beyond that. Okay? It's not an OH. An OH would be much broader and much more intense. Okay? Where I would say it actually gets more easily confused is not with the OH, but with the NH. The NHs tend to be a lot weaker in intensity, and sometimes sharp, sometimes broad, so they might be confused with that overtone. Okay, so just be kind of aware. If you see something and you want to label it, go ahead. Label it as an OH or an NH. So like I said, an OH is a bad call on this, but we might be able to call that an NH.
If there's no carbonyl, then and there is that signal there, then it's still going to be that will.
That is the if there was no carbonyl, then that would be the NH. Yeah, but we could have an amide functional group. What's the amide look like? It has both of them. It has the NH and the carbonyl. So there are possibilities where we could see circumstances where the NH and the carbonyl overtone mess with each other. Okay? So if you aren't sure, what should you do with the IR? You could leave it alone, or what I usually like to do, nice big question mark. Okay? Mark it so that if you get so absorbed in the HNMR and your brain loses all function, when you go back and look at the IR, you know not to trust that answer, okay, or what you wrote. Okay? Where should we move to now? The carbon NMR, which is where? Directly below it. What do we see in the carbon NMR?
Unique carbons.
We get 3 unique carbons. What can you tell me about those carbons? The far left is a carbonyl, and you know that because you look at the chemical shift ranges and verify that that's a carbonyl. Okay? How about the ones on the right? These are going to be alkanes. Okay? That's all I would expect you to write for your carbon NMR interpretation. Fast, loose, easy. Now we can move to the HNMR. Okay, this is where it can get kind of fun. Okay? So, where do you guys want to start? So, by 3, you mean the signal showing up at 1, right? Okay. What can you tell me about that signal? Try again. Try again. Try again. Try again. I can kind of see where I can accept the 2 unique hydrogens, actually. That's actually a step earlier than what I was complaining about. Still before that. There is a hydrogen. Simple. Keep it simple. Make it more difficult as you work. Okay? Now, what's the next thing you can tell me? It's an alkane because the chemical shift is in that really low range. So we're looking at a carbon, most likely. Okay? Now what can you tell me? Okay, which means what about my hydrogen? I would expect 3 hydrogens. Okay? Does it have to be a methyl? No, it could be 3 carbons with 1 hydrogen on each. Okay? The problem with that is that all of those carbons must now be identical to each other as well. Okay? That requires lots and lots of symmetry in the molecule, not particularly likely. Okay? Now what can you tell me? How do you know it has 3 peaks? Because I drew it on there. Okay? So let's pretend you don't see that. There's 1 peak, there's the 2nd peak, there's our 3rd peak. Yeah, isn't that fun to see? Okay, it's not always the easiest thing to see. This is coming from made-up data. It's computer generated, and they don't allow nice zoom-ins of each of those spectra, so you get what you get. Okay? So I zoomed in for you, and we saw that we have 3 peaks, which means what? We have what attached to our methyl? A carbon. Why is it a carbon? Because it can't be an oxygen or a nitrogen because we have splitting. Yeah. Okay? So we can put 2 hydrogens out there. Okay? Again, I would like to show the hanging bond. It's just my natural habit. Go ahead and throw that in there. Okay? So now what do? We can move to the other one. Okay, let's pick, what colors did I do that? Red and blue. Let's do purple and green. Okay, that's actually kind of a nice patterning. What's the first thing you can tell me about our second set of signals?
Hydrogen.
Good. What else can you tell me about it?
It's in the everything else range.
It's in the everything else range, so out of X.
It's not a carbon or a nitrogen. I mean, sorry, it's not an oxygen or nitrogen. It's
Why?
carbon because they're splits.
I'll accept that. We can decide that that is not a carbon or a nitrogen. This is in case you decide to listen to it online. We can decide it's not a carbon or a hydrogen, oxygen or nitrogen because it splits. That's a couple steps further down the road as far as our interpretation goes, but we can take advantage of that because we do have it in front of us. Okay. What's the next thing we can interpret about it? There are 2 hydrogens. And the last thing we can interpret, it has 3 neighbors. Easiest way to get 3 neighbors? We're looking at a CH3. Oops. Okay. That's all our HNMR tells us. So if we were going to go through and summarize everything, we'll do that in the upper left-hand corner. Okay, what did IR tell you you had?
SP3 and
So the CHSP3s is valid to mention, but our HNMR confirms that, so we won't specify that as an extra thing, mainly because I don't have a lot of space to write. Okay, what else does our IR tell us? We got the carbonyl. Our HNMR doesn't give us any information about that, so I will go ahead and write that down. It's a bit high up there. Okay, we could just leave it as a carbonyl. Again, I like to show the hanging bonds. How many bonds are missing in this? 2, 1 for each of those, for our carbons to get it to its octet. Okay. What did our carbon NMR tell us? 3 unique. Again, that's not an easy thing to summarize, so I'd kind of leave that one alone. What else does it tell us? Alkanes and carbonyls, also already shown, so then we could go ahead and summarize our hydrogen NMR. Okay. And one of the advantages to how we just went through and discussed this, particularly without a molecular formula, our HNMR told us we had those 2 pieces, right? Okay. So we now have a total of 3 pieces.
Cross with it.
Or we can put them both on the.
We just put it all together. There's no need to cross anything out. We just put it all on. Okay. Perfectly symmetrical, and we have an answer. So our final answer, if we looked at line angle, as it overlaps all the stuff I had down there, we end up with, what is that, 3-pentanone. Okay. She brought up an interesting point about crossing things out. Okay. This signal right here, our signal at 1, what hydrogen does it tell us anything about? What color hydrogen? Red, blue, purple, or what's now green? Red. That's the only hydrogen that this signal refers to. We were able to extrapolate extra information out of it, but this signal is only this red hydrogen. Okay. What signal shows up at 2.5? What hydrogen?
purple.
Only the purple. Okay. So what we might do is say, well, we've got these 2 pieces. These pieces have to be connected to each other. So more than likely, it makes sense to eliminate one of those. And in my summary, instead of writing those twice, I would just have this. Just those two pieces. Okay, does that make sense on how we're doing that conclusion? Now we've got kind of a problem though. We attach the ethyl to our ketone, and what happens?
So we have one.
We're missing a bond. Okay, well we could try and put an OH on it. Well, that would show up in our H or our IR and in our HNMR. So we can't add a hydrogen. We could try and add a halogen. Okay, that's one way to do it, but that makes an acyl halide. Those tend to be fairly reactive, also not particularly likely to be in there if it's something that's super reactive.
Assume it's a carbocation.
Okay. We could try and do a carbocation with it, except the carbocation is charged, and we typically don't take spectra of charged species. Okay? So we've got kind of a problem. So what do we do? Okay? If you run into this issue, what you do is assume symmetry and double something. Okay? We could double everything, but in the process of doubling everything, we'd also be multiplying 2 times our carbonyl. We'd end up having 2 carbonyls in the middle, and that would look kind of weird. Okay, it's possible, but that would just look kind of goofy. Okay, so it probably makes sense to just double our alkane piece, and as soon as we double that, we now have everything that fits together. Nothing is invalidated. We still have that 2 to 3 ratio, right? What's our ratio? 4 to 6 ultimately breaks down to 2 to 3. Our reduced ratio, remember, doesn't imply symmetry. It removes all symmetry interpretation. Does that make sense? Yes.
How do you know that's the structure as opposed to putting the ethyl group on the end and then putting an H on the other side since the...
If you put an H on the other side, what functional group do you have? Aldehyde. Which taken further, if you have an aldehyde hydrogen, where does that show up in your HNMR? At 10. We don't have it.
Don't have anything.
Well, that makes it easier. Okay? So now you don't have any questions about it, right? Does that kind of make sense as far as that interpretation goes? Okay. Should we go ahead and try another one? Okay. So let's see. Am I still connected? Yep. This one's extra tricky. Okay, and with this one, because I've got the space for it, I'll show you how I would go through and process it. Okay, so what we've shown so far, in my opinion, is rather cluttered. You're doing it all on the individual spectrum. It makes it kind of difficult to sort things out and interpret it. Okay, so instead what I would do is start to convert that information into a table where you can interpret from the table and try and piece things together a little bit cleaner that way. Okay? So, what information are we given in this case? Carbon and HNMR. What does our carbon NMR tell us? We've got 3 unique carbons. What can you tell me about those carbons? We've got an alkane. And now we're looking at alkenes or aromatics. Okay? The alkene and aromatics show up in virtually the same spot, so there's no real way to interpret which one's which from the carbon NMR. So we can then move to our HNMR. That's a bit interesting. Very, very simple spectrum. Okay? Particularly considering it gives us just 2 signals, and yet our carbon signal gave us more. Okay, so something seems a little bit weird here. Okay, so what I would go through and do as far as summarizing this is create my table, and I'd start with chemical shift. Okay, what signal do I want to start with? the alkane, is that what you said? Okay, so we can start with our tall one. Our chemical shift shows up about 2, so I'd go ahead and write 2. Then I would say structure. What does a chemical shift of about 2 tell me about my structure? What's the first thing it tells you?
There's an H.
We got a hydrogen,
Okay, so C.
and we're probably looking at a carbon. It's on the tail end of that 2 range. It's a bit dicey to go through there, but it's probably a carbon. What's the next piece of information? Our integration. This was a bit rude. I didn't give you all those numbers on it to help you interpret it. Okay. Believe it's 3. We're looking at a 1-to-3 ratio. We'll see how right I am in a little bit. I'm pretty sure I'm right. So we can then tablize that again. What does that tell us about our structure? We're looking at a methyl. That's nice. That gives us our alkane that our carbon NMR told us about. Okay, what's the next piece of information? Our multiplicity. How many peaks do we see? Where do you see your 3 peaks? So are you thinking here, here, and here? Not a bad guess, except
Is there one down?
that being pixelation. If you get those signals, and I'm not going to go back at this moment, but if you take a look, that's an eraser. If you take a look down below, you'll typically see that line drop all the way down. Okay? Showing that it's doubling back on itself. And if we take a look at that base, that's really open. Okay, which would suggest that our peaks, or we don't have a peak coming back down, filling in that white space. So what does that mean? No peaks, or no splitting, which means simpler, 1 peak. What does that mean about our neighbors? What does that mean about our structure? We have just a CH3. Okay. Now we could go through and interpret the next signal. Shows up where? We'll call that 6.8. What can you tell me about that? We've got a hydrogen connected to a carbon. What can you tell me about that carbon? It's aromatic. When you look at HNMR, the aromatic hydrogens have an additional ring current effect that causes them to shift substantially out of the range of an alkene, a standard alkene. So if you see anything in that roughly 6.5 to 8.5 range, 90% of the time it's aromatic and only aromatic. We're not looking at double bonds or anything else. It's an aromatic ring. Okay. Is cyclohexane aromatic? That's a bit of a stretch for you. You guys don't technically know that definition, but no. Cyclohexane is not aromatic. So if we have an aromatic ring, when we're referring to HNMR, most cases what we're saying is we have benzene. Okay? This introduces a bit of an interesting wrinkle in how we solve this. How many carbons does benzene bring in? 6. We're only supposed to have 3 unique. How many hydrogens does it bring in? 6, which means, again, we've got an issue. According to our spectrum, we only have 1 aromatic hydrogen. It's a bit odd. Okay, so let's pause on that for a moment. because our integration is going to be a bit difficult to kind of piece together there. Okay, so we might put a question mark. That's a question mark. An attempt at one. Let's try that again. What's our multiplicity? How many peaks do we see? 1, which means neighbors is 0. Well, if we go back and draw on our hydrogens for an aromatic ring, let's just be crazy and draw them all on here. How many neighbors does our now orange hydrogen have? 1, 2, 3 bonds. There's a neighbor. 1, 2, 3 bonds. There's a neighbor.
There's a methyl group attached.
So we've got to watch out for a couple things. At this point, what we've got drawn here is they're all the same.
All the carbons
Okay.
are two, right?
Yep. But can those all be possibly hydrogen?
No.
No. At very least, I have to add a methyl. Okay? And if we add that in there, now those hydrogens are only the same across the ring. How many neighbors does that now boxed hydrogen have?
2.
Has 2 neighbors. We get splitting. Crap.
CH.
Okay.
Every other one is CH3.
So what we have to go through and do is evaluate lots of symmetry in this structure. Okay? And so what you were able to piece together was the answer for this. Somehow or another, when we look at our aromatic hydrogen, okay, remember our ratio is the reduced ratio. We're looking at 3 to 1. Okay? So when I draw out my benzene ring, if I put on a CH3, I have to put on a single hydrogen. What about the rest of those positions? Well, I could put on another CH3 and another hydrogen and another CH3 and another hydrogen. I've maintained my ratio. Does that substitution pattern explain everything? Do my CH3s have hydrogen neighbors? Nope. Do my hydrogens have hydrogen neighbors? Nope. My integration ratio is fine. I have my aromatic hydrogens. I have my alkane hydrogens. How about my 2 aromatic carbons? One that has the hydrogen, one that has the methyl. Okay? What if you didn't happen to chance into that along those lines, and instead of doing the CH3, you put a hydrogen there and then did CH3? Say something like this. That maintains the same ratio,
With the neighbors on this stuff.
but now we lose the symmetry. This hydrogen is different from this hydrogen, and they see each other as neighbors, which means we see splitting. Okay? So one of the things that's nice with aromatic rings is it nails down a lot of carbons and a lot of hydrogens almost instantly. Okay? And what you can do is try and interpret, because in most cases you don't have this amount of symmetry. This one's kind of a trick question because you got a lot of symmetry through this molecule. You can count up your integration for your aromatics, and if it says there's 4 hydrogens, what does that mean? Try that again. There's 4 hydrogens in your aromatic region. What does that mean? 2 groups on your aromatic ring must not be hydrogen. So that if I looked at my aromatic structure, I could go through and say that my bonding pattern was something along these lines, where that's an X and that's an X. That's going to give me a very characteristic splitting pattern for the rest of the hydrogens on there. I could also do something along these lines. X, now maybe it's Y over there. That's supposed to be a Y. Okay? Or maybe they're next to each other. And it may seem a bit daunting at the amount of possibilities there. It's actually fairly few. Okay, particularly when you consider how many ways you could combine an individual formula to make a different compound. Okay, so when you see an aromatic signal, that's usually one of the first things that I jump all over and interpret the heck out of that signal as best I can, because that will nail down and simplify the rest of my solving process. Okay, so I'll even jump to aromatics ahead of multiples of 3. Okay, that said, I think this assignment doesn't have any aromatics in it, just so you know. Okay, no, that's not true. One of them does. It's a hard one too. Did it actually start working? No. Okay, I've got one more if you want me to go through and solve it. If you'd rather just work on the assignment, ask questions, talk to each other, figure out what's going on with it, I'm fine with that too. Kind of leave it up to you guys. What do you guys want to do? Leave it after this one? So solve this one? Okay. So, first person to speak up wins. So, let's go through and evaluate. We start with our IR. What does our IR tell us?
CHSP3.
Anything else? There's an awful lot of peaks down there.
Can't see any of the numbers.
Go for it.
1500 is right there.
Right.
So pretty much all of those signals in our fingerprint region, there might be a lot of peaks down there. I wouldn't touch any of them.
Really? Not
Okay.
even above 1400?
Nope. There's just too many things that could be there. You might see some aromatic stretches-ish,
Exactly.
but your aromatic usually shows up at 1650, I believe, and there's no peak above 1500, so you can't have the
Don't make
aromatic.
life more complicated.
Exactly right.
And at that point, could we just look at our HMR and see if they have these between?
And then you could jump to the other things to interpret. So that's why I would leave the IR alone, keep it really, really simple. And if I find out more information, like if I find out there's an aromatic ring, then I might go back to the IR and be like, okay, I know it's supposed to be here, and my TA is probably grading for it, so let's just say it's here. And just pick some random peaks and assume that whoever's grading it probably doesn't know what we're grading anyway. Okay? Which is not a bad bet, if you didn't have me, just so you know. I'm actually pretty good at IR. So we could then move through to our carbon NMR. Our carbon NMR I decided to put in a nice small section there. How many carbon signals do we see? 4. We get 4 unique carbons. What can you tell me about those carbons? They're all pretty much alkanes. Okay. This one actually looks kind of familiar too, slightly different. Okay. Now we can move to our HNMR. How do you guys want to process? Do you like the table, or do you want me to just try and draw on the spectrum? Okay, so we kind of go through and draw on the spectrum. Where do we want to start? Oh, I forgot. I didn't show integrations or the splitting nicely on this. Shoot, so now I have to do this in my head. Crap.
So can you write down 6.38, 1386.
Which number are you doing, 2A?
Yeah.
I don't have
So
it. Is this what you're going with?
That's it.
Didn't think that mine was similar.
It kind of is and it kind of isn't. So 6233. Sorry. I just confused all of those numbers in my head.
1, 2, 3, 3.
Thank you. 1, 2, 3, 3. So I'll give you that integration information for this one. Okay. So where do we want to start? So our far right. Okay, so for that signal, since we got 4 of these, might as well go ahead and do it in color. What can you tell me about that signal? We have a hydrogen. What can you tell me next? What? It's connected to a carbon. So we have 3 hydrogens. What else can you tell me? Oops. Has 2 neighbors. So we've got atom X with 2 hydrogens. What is atom X? It's going to have to be a carbon because... Could be. We could run with that. sp3CH. Why else does it have to be a carbon? Nitrogen and the oxygen would hide it. Or hide those hydrogens. Okay? So we have a possibility. What should we do next? Okay? So here's where I'm going to cheat a little bit. Okay? In the process of solving that first line, or that first sample at number 1, I just identified new hydrogens. Okay? Which means, if I'm doing this correctly, if I solve that signal at 1 correctly, those red hydrogens must show up somewhere else in the spectrum. So instead of just jumping or just moving sequentially through to each signal, I'm going to look for those red hydrogens and find the signal that represents them. Okay? So before I start looking for it, what do I know about those red hydrogens? Okay, they're alkanes, so we would expect a signal on the low end of our chemical shift, but all of our signals are low, so our chemical shift isn't going to help out. We've got at least 3 neighbors, okay, and that's at least is massively important. I have no idea what's attached to the other end of that carbon. There could be a bunch of other hydrogens out there, which could change the splitting pattern. Okay, so when I go back through and look for my signal, what I need to look for is a signal that has at least 4 peaks. It could have more than that, but it will not have less. Does that make sense? So I need to look for something that has 4 peaks, but 4 peaks is multiplicity. There's something easier than multiplicity to look for.
Integration.
We could look for the integration. What do we know about the integration? Has to be 2. So we go through the rest of our data. I've got a signal for 3, 2, and 1. What does that mean? Gotta be the 1, 2. Okay? So I can now try and process that one. And we'll go ahead and call that our red one. And I can say I've got those hydrogens. Okay? So we're kind of cheating there and jumping through this, the chemical shift and integration. But now to the splitting. So pretend you actually don't have this one nicely shown in front of you. Let's look at the one we've got here. Okay, and I'll kind of attempt to draw a zoom in for that. We'll show it in red in the upper right-hand corner. What I see is a peak, taller peak, way taller peak, way taller peak. What's the splitting pattern? So first off, these 2 are probably not part of it, right? Okay, those have to be a separate signal. So in theory, we were nice enough, or I was nice enough to tell you that we had 2 signals there. Okay? But then what you're trying to interpret is if we take a look at the tallest peak that we think is part of it, is that the absolute tallest peak? Or is there a taller one after it? Okay, we don't really know. But what we can do is go through and say that there has to be at least 1, 2, 3, 4, 5 peaks. Bare minimum. Why do there have to be 5 peaks? It has to be symmetrical, and what we assumed was that that arrow peak was our tallest one. Does that make sense? Okay? So that's a bit rough to go through and make that assumption, but we can do that. Okay? If you aren't comfortable with it, don't make that assumption. Toss up your hands, move on to a different peak.
That'd be the 14641.
14641. Is that what you said?
14641.
Yes. Okay. So let's go ahead and stick with that assumption first, because if it did indeed have another tall peak after it, say one that was in here, We would then expect a short one to match, but then we'd also expect a short one to match on that outside. And we don't see that. Okay? It's not really fair to completely eliminate it or toss that out the window because those two tall peaks are taking up enough area they might still be hiding. Okay? But that seems like a reasonable guess. So what we're going to assume is that we have 1, 2, 3, 4, 5 peaks. If we have 5 peaks, what does that mean about our neighbors? We have 4 neighbors. How can I get 4 neighbors?
One more each.
I could go through and put in a CH3, which, remember, we jumped to this signal because our first signal gave us information about it. So we better have that 3H there. Okay, I need 1 more hydrogen. So what can I do?
We know there's no oxygen because of the ion, or maybe we know there's no oxygen, so we can just add carbon and 1 hydrogen.
We can add a carbon and 1 more hydrogen, and we don't have to worry about the oxygen or nitrogen at all. Why not? They're splitting. Okay? That carbon, 2 extra bonds on it. That's pretty much all we know about it. What's nice about the method that we're starting here is what did we just now find? We found another hydrogen. If I did all the analysis correct, this new hydrogen better have a signal somewhere in my spectrum. What do I know about my blue hydrogen? It has at least 2 neighbors, and there's only 1. So now I can go back through my integrations. I already covered 3. I guess I can do these in the right colors. We already covered the first 3. I already covered the 2. So now I've got 2 signals left. 1 that integrates to 3, 1 integrates to 1. If I did everything right, that blue one had better be 1 that integrates to 1, right? Okay. So let's see. What information do we have from our spectrum? How many peaks do we have for our signal at 4? 2, 3, 6. I see 6 peaks, which means how many neighbors? 5 neighbors. How many neighbors do we currently have shown? 2, which means I'm going to have to get another 3 neighbors on there. What's the easiest way I can get 3 more neighbors? A methyl. So I can add a methyl to one side. I could split this as a CH2 and a CH. Okay, that is a possibility. I do have those 2 slots. I don't want to do that because that's a lot of extra work. Okay, that's making it more complicated than I have to right away. Okay, what's nice about this? Yes, that's not quite where I was going with it. We just found more hydrogens. If I analyzed everything correctly, these hydrogens better have a signal somewhere in my data. So I can go back to my data. What do I know about my green hydrogens?
3.
There's 3 of them, so I need to have a signal that integrates to 3. What else do I know about them?
1 neighbor.
They have 1 neighbor, which means how many peaks? 2. So I should expect to find a signal that integrates to 3 that has 2 peaks. So I go back through my data. I only have 1 peak left over. It integrates to 3, and it's got that weird overlap. Okay, but if we go back and evaluate it, if we look within that overlap, what does that look like to you? 2 peaks. Okay, one might be a little bit taller than the other, but that makes sense because we might have had some overlap shifting into it. Okay, constructively adding to the size of the signal. So what does that mean? HNMR is now solved. So, don't quite want to answer that one directly, but we've got our CH3, we have our CH, CH2, CH3. We're missing some bond. we'd have to go back to the rest of our data and hope we could find some information about what that bond might be. If we don't have that information, what should we do?
Put a question mark.
We already talked about it. We did it earlier. Don't have that information. Still don't have that
You
information.
assume symmetry.
Assume symmetry and double. Double it, and then we can go through and put in a CH up here, CH2, CH3, CH3. Okay? That's all the information we got, so we have to somehow seal it off. We can just go through and double it. That's valid based on the information that we have at hand. You guys have different information than I have. So we'll just leave it at that. Okay? Does that make sense? Okay. Questions about that? So we went through and spent, according to the timer, 80 minutes now, and we saw